Here we have a scenario where we have a rocket that is being interacted with Earth's gravitational force over two different positions. We have one position it's initially at, and we have its final position, and we have the time it took to get there. We want to see what kind of change in gravitational force we find over this time. So we're given the masses of the Earth and rocket Sega, and we want to know what is the difference in the force that is acting on rocket Sega from time 1 to time 2. And we want to see, at the end, we want to find the average change over that period of time. So we want to recall and look back to find our momentum principle that we can relate at the end. We need our gravitational constant G, and we're given a little bit of information here. We're given our change in time. We found our vector for our first position, which gives our position for the rocket to the Earth. We subtracted the vector of the position of the rocket's initial spot from the vector of the Earth's position, and that gives us this vector. We did the same thing for rocket Sega's second position, and we found the unit vector from rocket Sega to Earth here. So we have our initial position of rocket Sega, and we have our final position of rocket Sega. So we have our unit vectors calculated. We calculated them in part 1 in standard 1, and we found that our unit vectors do change over these two different positions, and so the direction of the gravitational force will be acting on rocket Sega in a different direction because it's a different unit vector. So we're going to subtract our initial gravitational force from our final gravitational force of the Earth acting on rocket Sega. So here we have our gravitational force formula. It says that negative G times the mass of Earth times the mass of the object, in this case rocket Sega, times the unit vector, all divided by the magnitude of the position from the rocket to the center of the Earth squared. So here, this is what we're going to do. It's all written out in the formula. All we need to do is plug in and solve from here. Our change in gravitational force averaged will be the gravitational force of the final position where the Earth is acting on rocket Sega minus the gravitational force of the initial position where the Earth is acting on rocket Sega, and then we're going to divide that difference by our time interval of 2,500 seconds, and it's going to give us negative 0.176, 2.990, 0.352 newtons per second. So observing this vector, if we look at the change in gravitational force over this time period and this distance per second, we can see that over a long period of time, even a period of 2,500 seconds, that this force of gravity can change pretty dramatically. It might not be great to do a written calculation like this using the momentum principle to find the change in momentum of a problem like this, because it's going to be pretty off. You can do it, but I think it's safe to say for this kind of a problem it'd be much safer to do a numerical calculation that could get a much more accurate result for the change in momentum of rocket Sega while passing by Earth.